Okay, ready or not?
I already put the link, but I think we should wait
Okay, great.
a minute. Okay, I think we can start.
Okay, great. So as I promised yesterday, I will do a small corrections of exercises each day after the break. So yesterday on Discord, I suggested you to look at exercises 1, 3. So they are at the end of the PDF, which I sent yesterday. So maybe some of you did the job. And but anyway, here are brief corrections. So the first exercise is a variation on the so-called De Morgan laws. Okay, but actually it's more general than that, but it's motivated by this. So De Morgan law in logic says that the negation of disjunction is the conjunction of the negations. So if you believe me for a moment that plus is a disjunction or has to do with disjunction and that times has to do with conjunction, if you believe me that A implies false is a way to express the negation of A, okay, then this type here, which is displayed in exercise 1, so this type here, expresses this De Morgan law. But actually, so we here it's an example of logical equivalence. So we only need to provide a function from here to here, and here the 0 plays absolutely no special role. So it could be as well any C here. Okay, and it's obvious how to build such a function from A plus B. So if you have a function from A plus B to C, you need to find a pair of functions from A to C and from B to C. But the first one, you obtain it by, remember that with the plus type comes the in left and the in right. So in left is something that goes from A to A plus B. So suppose that you have a function from A plus B to C, you just have to post-compose it with in left. Okay, so you first, it's post-composed because of the notation of composition, but it means actually you first go from A to A plus B with in left, and then from A plus B to C by the function that you have here. And the same here, so you get clearly a pair of two functions which have the right type. So this is for exercise 1. And exercise 2, okay, so it's it is, you can see it also as a little formula from logic. Okay, if you know that for all x you have two predicates that hold, px and qx, well, it implies that for all x, px holds, and for all x, qx holds. And the proof is very, very similar. Okay, so suppose that you have a function, you know that product comes with projections. Sorry, these exercises are really easy, but there will be less easy exercise. Well, the ones that follow are not so, well, not all as easy. So we know that we have these projections, okay, and the other one. So if I have my function f here, okay, I need to find a function here, and this function will be lambda x dot PR1 of fx. It's as simple as that. And same for the other one. Okay, so I don't think there is anything serious here. And the exercise 3, actually, I provide a solution in the slides. So I can just read what the exercise does, well, asks you to do. So the exercise asks you essentially to encode. So remember that I gave fin of n and can of n, and then a function max, and then a notation that can of n. So remember that I gave a notation that can of n is the set 0 n n minus 1 n. Okay, this was all notation, and it was all only suggestive. So this exercise shows that with the type theory that we already master from the course, we can make all this formal, okay? And the idea is to define can as a function from a family of types, okay? So a function from n to u, the universe u. And this can be defined by induction on natural numbers, by saying that can of 0 is 0, because the type 0 is what represents the empty set, or the empty finite set. It's the best representative somehow. And then you can define can of sux n to be the co-product of can of n and 1. Okay, so essentially the canonical set with n elements plus another element. So then you have n plus 1 elements. Okay, so this is a definition, and then we can define fin of n as the type which says it's a pair of a type A and a proof that A is equal to can n in the identity type of the universe. Okay, so this so far are only definitions, and the exercise requires you to define the function max and these notation here, in. Okay, and for this notation to be properly defined, you also need to define a predicate, which is you also need to define a type. So it's a family of type x less than y, or x x strictly less than y, or than y, sorry, or x less than or equal to y. And this is a type family because okay, so this type family goes from nat times nat to u. Okay, so you fix an x and y, and then you have the type x less than y. And this again is, well, and you need this in order to define this function in properly, because of course this makes sense. This in here makes sense only if I, so this is here an in. This is here an in. This makes sense only if I is strictly less than n. So you see that this predicate must appear somewhere in the formal program that will produce it. Okay, so the exercise is to define these two functions properly, and the predicate is defined here. So I can comment on the predicate if you want. So on this family. So you define this again by induction. So you define I will just define less than or equal. So you define it by induction both on x and y. So you first consider the case where x is 0. And then in this case, you say that by definition is a type 1, which says, okay, this is true. And then if it's a sucks, okay, you will also you will start an induction on the second argument. So if the second argument is 0, then the value of this family at x and at at sucks x and at 0 is a type 0, which means, okay, this is false. And then, okay, and then the case where both are sucks, okay, then the type here will be defined to be exactly the type x less than y. Okay, so, and then the solution, you can read it in the slides. Okay, so now let's return to where we were. I think we were somewhere near page 40. Yes, yes. So there were some discussions. Maybe I didn't read all the discussion after, but there were some discussions about why these two types. What does it mean that these two types are logically equivalent, and why would they not be equivalent? Okay, so what I have just shown you is how to define a function that maps by inv of f to q inv of f, or conversely. So it takes data in by inv f, okay, which is a quadruple of a g, an epsilon, an h, and an eta, okay, and does something and returns an element. So it's really a function from here to here and a function from here to here. What is missing, what does not actually hold, is a proof that these two functions are inverse of each other in the sense of homotopy. So what is missing, and in fact does not hold, is the fact that these two functions. So here we are at another level. We are at the level of trying to prove that these two guys are logically equivalent. So we defined a meta function, a big function h here, a big function k here. And what is missing here is a proof that k composed with h is a homotopy to the identity from q in f to q in f, and conversely. And in fact, this does not hold. Okay. And I will not prove it in the course, but I will discuss this further, well, the consequences of this further later. Okay, so, well, so good. So now let's take back the course, the normal course of the course. And what I promised to do right after defining transport was to play with transport and try to give some properties of transport. So there was a question on Discord on whether there is a unique way of defining transport. So I don't know exactly how to answer this question. I would rather speak here of a canonical transport being defined by induction is sort of canonical, and same thing for app and same thing for appd. They are canonical way to achieve what they want to do. Okay, transport wants to transport, app wants to be functorial. Okay, appd wants to be functorial in the dependent sense, and it does the job, and it does it's defined in a very canonical way. I cannot say anything more at this point. Okay. Good. Properties of transport. Here we are. Okay, the first thing here is okay. The first thing here is what I thought I had not written. Okay, but remember that by definition, because transport is defined by induction, so this is clearly one thing that we want of transport, and the way to define it allows us to make sure that this holds. So namely, if you transport along reflexivity, then you do nothing. Okay. The second property is that if you transport along a path, here, P, and then continue to transport along another path, Q, this is the same as transporting from along the concatenation or composition of these paths. But again, is the same is in the sense of being homotopic. So these are two functions that, well, if P was going from, let us give types. If P is an equality between X and Y, if Q is an equality between Y and Z, then this function here goes from Cx to Cy, then from Cy to Cz. So this is a function from Cx to Cz. And of course, here also it's a function from Cx to Cz. And what we ask is that these functions are homotopic. So point-wise, they are equal in the propositional sense. That's what this property says, and it can be proved. And how can it be proved? By path induction. Okay, I will not do all the proofs because they all look the same. Well, except when they are a bit tricky, like the one of Christine Paulin. Okay, so next property is that if you have a type family B, and if you have a function from A to B, then you can compose C with F, okay, and you get C composed with F, which is another type family, but indexed by A, not indexed by B. And so you can, if you have now a path from A1 to E2 in A, okay, you can apply it by F because we already know application, okay. So maybe I did not mention, but I also use, because it's heavy to write app FP. So sometimes I allow myself to write just F of P, because actually it's S is a functor, so it should apply not only to points but also to paths. Okay, so F of P is just an abbreviation for this. So I can do S applied to P. That gives me a path from F of A1 to F of A2, which lives in B, and I can transport along this path with respect to the family C. So it means that this U here is taken in C of what? It's a good question. C of F of 1, F of A1. Okay. And F of P is an equality, yes, and this whole thing here lives in C of FA2. Okay, so you can do it in this way, but you can also do it by first changing your type family. Okay, now you have C composed with F, so it's a type family indexed by A. And something is no, it's okay. Yes. So this U here So let me call this family D here. You can transport along P with respect to this family, and then this U should belong to D of A1. But by definition, D of A1 is C composed with F, so it's the same. Okay, this type checks. And it's clear that we want this, and we can prove it by path induction. Okay, so now here is a very interesting property that we will need later, is sometimes and quite often we take families of types which are themselves equality types. Okay, so this trick will happen quite often. So suppose that our family of types is exactly this one. It fixes some A1 in capital A, okay, and it maps X to the type A1 equals X. Okay, so it's a family of types, because this is a type, this thing here is a type. And then we may ask ourselves, what is the result of transporting with respect to this family C along a path P that goes from A2 to A3, okay, an element of CA2. So what is an element of CA2? It is a proof that A1 is equal to A2. So there's a very simple way to get an element of CA3, namely to concatenate the proof Q, which goes from A1 to A2, and then the path P, which goes from A2 to A3. So this guy is correctly typed for being the result of transporting. And again, because this is something that seems quite natural, then we pretend that it's true, and then we show it by path induction, and it works. Okay, so these are three easy properties of transport. Now, there's something a bit more technical, which I might not give in too much detail. I don't know. No, I will try to. Maybe not in full detail. So I want here to stress that there is a slight mismatch between the definition that we gave of app in the non-dependent setting and app D in the dependent setting. So let me first give evidence that there's such a mismatch. Okay, so suppose that I have an F from A to B. Okay, I first, before defining transport, before defining app D, remember that I defined app, and app was defined like this. Okay, well, the type of app was defined like this. F takes, so yes, my P is from X to Y. F takes X and Y to Fx and Fy. And app Fp should be proof of a path from Fx to Fy. Okay, and we defined it by induction, and it has this type. Okay, now this arrow type is actually a special case of pi type. Okay, so we could as well have tried to define app D Fx. Okay, by pretending that B depends on A, even if it depends in a fake way. Okay, so we have this family, constant family of type, lambda x A B. And app D Fx, according to our definition, is a proof that transporting relative to this constant family along P, the element fx is equal to fy. So you see that this guy here is not this guy. But we can prove that they are equal. But this is propositional, okay? So it's not definitional. So these two guys happen to be equal. And so this is the second part of this slide. So we can show by path induction the existence of a path from this, well, it has nothing to do with f of x specifically. It's for any b in B. We can show that transporting what did I write? Is this correct? Yes, transporting, yes. If the family, if the type family is constant, well, the point is that why should we care about transporting in a constant type family? Okay, maybe I can go back to my pictures. Where were my pictures of transport? What? Why did it disappear? That's strange. It's strange. Okay, so no, can't find it anymore. So let's yeah, so let's make the picture very, very small. So the picture was like this. Okay, and then I noticed that somebody was living here, okay, and who somehow had to communicate or speak with somebody here. So I had to transport it because here I had some bx and here I had some by. Okay, but of course, if this is a constant family, all these guys are the same type. So this guy lives also here. So you see that you morally speaking, you don't want to transport in the constant case, in the non-dependent case. But still transport is defined by path induction. So it's something, and you cannot just say that they are definitionally the same. So you need also to prove by path induction that they are equal. Okay, and this is what is done here. Okay, so we can prove by path induction that we have an equality, essentially that transport doesn't do anything, but here it's propositional. Okay, and then we can show that app D and app are related through this coercion. So you can think of this as a kind of coercion that coerces this to this. And hence, what we can prove is this property here. So maybe I put some. What we prove is this property here. One can prove this property here. That app D is obtained by concatenating this witness of coercion with app. Okay, so you see that we can make also all kinds of coercions very explicit in homotopy type theory. Okay, but I don't think I'll make a real technical use of it in the course, but I will mention you somewhere where actually it is used, but I will not go into the details. Okay, so next thing was to play a little bit with this notion of homotopy. Remember that before the break, I tried to justify all these manipulations here, here, okay, and this is here. This is all recorded here. So, for example, we need to prove the transitivity of homotopy. Okay, so if F is homotopy to G and if G is homotopy to H, we need to have a witness that F is homotopy to H, and this is this doesn't need an induction. Okay, well, not directly. So in order to define this homotopy, well, you just have to do it pointwise. So pointwise, you know that you have a proof that fx is equal to gx and a proof that gx is equal to hx. So you just concatenate them. Okay, here. And of course, concatenation is defined by path induction. So there is some path induction involved. And this, you do it for all x, and here you get something of the right type. Okay, now very similar arguments. I'm not going to detail them, but for very similar, with very similar arguments, we can show that homotopy is a congruence in the sense that if you post-compose with some k, okay, if F was homotopy to G, then the post-composition of F is homotopic to the post-composition of G with the same K, and the same thing for a pre-composition. Okay, and these are mostly what I used, actually, I think, in my argumentation that Q inv and B inv are logically equivalent. Okay, good. So now we move on, and our next objectives will be to try to know more about identity types, and somehow the question that we want to ask, maybe I write it down here in a new slide. Yes. The question so it's a general question here. Can we somehow define the equal A by induction on the structure of A? So for example, suppose that A is a sigma type. Is it possible to express A equals A times B in terms of something simpler, which is A equal A and equal B? And we can ask similar questions for other type constructors. Okay, so that's the general plan. And let's do this for the product types. And this works fine. This works fine. We can prove that these two types here are equivalent. Not only logically equivalent, but equivalent. So in other words, if we want to prove that X and Y are equal, well, you just have to prove that their projections, first projections are equal and the second projections are equal. Okay, so how do we prove this? So we need to find, remember what we need to do, we need to find a function from here to here, a converse function from here to here, and a proof that they are inverse up to homotopy. So we have to define these functions. So in this direction here, it's easy. You take a P, which is of this type, okay, and then you, because PR1 and PR2 go, maybe I should write it, PR1 goes from A times B to B to A, okay? Hence, it is a functor. Hence, I can apply PR1 to my proof of X equal Y. And what I get is a proof that PR1 of X is equal to PR1 of Y. And the same thing for PR2 equals PR2. So I have this very simple function in one direction. In the other direction, I will need to be a bit more careful. So it's a function from a product here to some type. And remember that we had an induction principle for products, which is simple, but it's still an induction principle. It's that we, in order to define this function, we can assume safely that what did I write? Yes. Yes. So we can assume a lot of things. We can assume a lot of things. Here I have a blue and red code. So the blue code, okay, involves X and Y, which are both elements of A times B. So by induction on products, it is safe to assume that X is an explicit pair AB and Y is an explicit pair A prime B prime. Okay, and now the red code here, because here I have also a product here, we can safely assume that an element in this type consists of a pair of a proof that P is a proof of this and Q is a proof of this, okay? But since previously we assumed that X is AB and Y is A prime B prime, this definitionally, this guy is definitionally A, this guy is definitionally A prime. So it means that I have a proof that A is equal to A prime and a proof Q that B is equal to B prime. So this double induction on two Cartesian products, this one and this one, reduce my problem in finding a proof that AB is equal to, sorry, I continue. So far I reduced to X being a pair, Y being a pair, and an element here to be a pair of a P and a Q. So now, because P and Q are separated, I have access to P and Q, and because all these things are varying, okay, this is for all A prime, etc., I have access to path induction. So I can reduce my problem to P being the reflexivity and Q being the reflexivity. So in other words, in order to define this function, all what I have to do is to consider the case where this is pair of AB, this is again pair of AB, P is ref and Q is ref. Okay, so I need to find an image for the pair formed by ref A and ref B, which should be a proof that X is equal to X, because this Y has become AB, which is X. And for this, I just take the reflexivity on the pair AB. So it's a proof that AB is equal to AB. So we reduce the problem to a very special case for which we have an evident solution, namely ref, and that gives me for free the definition in the other direction. And then we are not over. We have to prove that this function defined by these inductions, and this function defined directly are quasi-inverse of each other. And again, this can be done by path inductions, and you have just to be careful in which order you make them, but I will not do this in too much detail. Well, I will not do it at all. Okay, so now what happens if the product is in fact a dependent one? Sorry, a dependent sigma type. That's here. Okay, so I will not detail, but we can prove again that we can prove that the equality type W equals W prime in this type is equivalent to this type. The type of pairs of a proof that PR1W is equal to PR1W prime, and a proof that using transports, here we need transport because we are in an independent setting, a proof that PR2W is equal to PR2W prime up to, well, with the necessary transport to make this meaningful. Okay, so this is good. Now I give another example. Can we characterize the type, the equality on 1? Okay, so here we will not reduce this to a smaller type because 1 is already a very small type, but we will prove that the equality type x equal y for arbitrary x and y of type 1 is equivalent to the type 1. Okay. So it's another way to say that equality types sometimes can be avoided because here this doesn't refer to equality type. Okay, so let's do this proof. So we have to find maps in the two directions first. So one direction is easy. Suppose that I want to go from here to here. That's easy because I have one special element in one, which is star. So I can take the constant function that takes any p of a path from x to y to star. In the converse direction, okay, it's a good exercise in induction on the type 1. So we have to define a function that goes from 1 to x equals y. Okay. What did I say here? Yes, sorry. This is not correct here. It's a typo here. So this should be corrected. This type family is from 1 to u. Okay. And it's defined by applying, so B applied to Z, where Z is of type 1, is the type X equal 1 Y. Okay, so it's a constant type family. Constant type family which maps into the type X equal Y. So what we want now to do is to define a function from 1 to X equal Y. So by induction on 1, it's enough to find an inhabitant of this type because induction tells me that once I know the value on star, then I have the whole function. So my goal now is to establish that I have an inhabitant here. Okay, but I'm not in a very good position to find this unless I first try to do something more generic. So I will first exhibit an inhabitant of this type, which is clearly more generic. It's a type which is parametric in xy, so it's pxy x equal y. So this is my next goal, to find a guy here. If I solve this goal, okay, so if I have a value for this guy, then I will define this guy by applying so this is box 2. And if I have box 2, then I have box 1 defined in this way. Apply just box 2 to x and y. So my goal now is to define box 2. Okay, so here we are going to do an induction on 2 inductions on 1, because this is a function that takes 2 arguments of type 1. So first I will fix my x here. X is supposed to be fixed, and y is fixed. And I consider the type family, which at x, Cx is by definition Pyx equal 1y. Okay, so by induction on 1, so my problem gets reformulated at this stage. My problem gets reformulated to find a guy in this type, Pyx Cx. Okay, this is repackaging. Yes. Okay. So I need to find some guy here. Okay. And for this, I will use induction on 1. So what I need is to find an element of C star. Okay, just the value of this function that I'm looking for at star. So my next objective is to find the box 3 in C star, which is because the x is here, it's the type, this type. So we need now to find a guy here. Okay. So again, how do we find this guy? By induction on 1. We only need to find a value when y is star. So we need to find an element in star equals star. Okay, that's box 3, but it's easy. Take the reflexivity. Okay, so box 3 allows me then to define box 2, which allows me then to define box 1. So you see that I have used the red induction on 1 to define box 3, then the blue induction on 1 to define box 2 from box 3, and then I have used just a simple function application to get box 1 from box 2. Okay. And finally, I have used box 1. I have used the purple induction here on 1 to derive from box 1 the desired function that goes from 1 to x equal y. So you see, this function exists, but it takes a little while to define it. And then, of course, it's not finished. You have to show that these 2 functions are quasi-inverses, and this I also omit. Okay, so why did I do this now? Because then it is natural to ask the same question for other kinds of type formers. So what happens with co-products? So we will see that later. We can also somehow reduce the equality with respect to the type A plus B in terms of equality in A or equality in B. But this will require another method that I don't want to introduce now, that I will introduce later, which is called the encode-decode method. And this, I might do it on Thursday, I believe. Okay, so I'm not going to do the sum type, but it can be the co-product type, but it can be done. So now, what about function types? And what about identity types? So the question is, can we characterize what is the equality between functions in the proposition sense? So here, actually, we cannot prove anything. So when we cannot prove anything, we give a postulate. So we augment our type theory with one axiom, which is called function extensionality. So how to read this? So we assume as a postulate that f, the propositional equality of f and g, is equivalent to something that we have defined, which is homotopy. And homotopy is really respects the idea of defining things by induction on the structure of types. Because remember that this means that fx is equal b to gx for all x. So you see that here this homotopy really refers to equality for smaller types. But nothing in principle tells me that these two things are equivalent. So what is written here is not completely precise. So what we actually assume, and this will be done in the next slide, we will assume that the function that goes from here to here and that is easy to define canonically has a quasi-inverse. Okay, so what we will assume is that this function that we will introduce in the next slide, which I call h apply of fg. Why is it easy to define such a function? Because it's a function from an equality type. So we can, in order to define it, we can just do it by path induction, which we will do. While from here to here, there is no tool. I don't know how to do this. Okay, so what function extensionality says is that we have q-inv of h apply ft. Okay, so this is what this axiom tells, and I will say it formally in the next slide. And next comes probably the most emblematic axiom of homotopy type theory, which answers the question of characterizing the equality for the universe. So it's an axiom that will say that being equal propositionally in the universe for two types, so arbitrary types will be equal. This is one type, and we are going to assume that this type is equivalent to the type expressing that A and B are equivalent. So what is this type? It's written here. It's a type which witnesses that A and B are equivalent. So it's a pair of a function from A to B and a proof that f is bi-invertible. Okay. And here again, there's a big warning. While q-inv is somehow the natural thing to do, if I put q-inv here instead, then, as we shall see, probably tomorrow, type theory becomes inconsistent. So here it's serious business. That should indicate that q-inv is really not the same thing as bi-inv. It's the same thing in the sense of logical provability, but not in the sense of equivalence of types. Okay, so let's let's it's just a warning that here it's not by case that I put by inv. I put by inv and not q inv, and we will say more on this later. Okay, so anyway, the story is the same. Because this is an equality type, I have a natural function here defined by path induction. And what I require is that this function is an equivalence. And for this, I can use qinv or byinv or whatever notions logically equivalent. But okay, at this level, to show that they are equivalent, I can use any of the qinv and byinv, and we will see two other such things. But one thing is to prove that they are equivalent, and one other thing is to internalize this notion inside a type and to give an official type. Okay, this is another level. And when internalizing, then we have to be very careful, because these guys being logically equivalent doesn't mean that replacing one by the other, these different notions of a type of equivalence, because this is now a type, and these types are not going to be in general equivalent. So it really matters what we choose. And if we choose it well, it works. If we don't choose it well, it's inconsistent. Okay, so with this warning, let's move on. And this axiom is called univalence. So if we do not stress too much about B inv versus Q inv, what we can remember at this stage is that this principle, what does it tell? It tells us that once you proved that two types are equivalent, or if you prefer, are isomorphic, because after all, this is what equivalence is. You have two inverses, okay? So if two types are isomorphic, then they are equal. And this is very powerful, because being equal means that I have access to all kinds of tools related with equality types. I can, if I have a structure on one of the types, like this type is equipped, I don't know, with some mathematical structure, and if I know that they are isomorphic, I know by univalence that they are equal, and by the power of equality types, I will magically be able to say that automatically B carries the same structure as A. I will illustrate this later with an example. But this is one of the examples of application of univalence, namely that it helps to carry structure from one type to an isomorphic type, additional structure. I mean, the isomorphism relates the types, but not the additional structure. Suppose that they are isomorphic, that A has additional structure, then you can transfer this additional structure to B thanks to univalence, because you go to the level of propositional equality, and this helps you to transfer the structure. So we will see this later in practice, but this is the idea. Okay, so now let's be more specific on how to define these canonical morphisms that go from the equality type to its claimed characterization. Okay, so I want to define both this H apply and this guy, I give it a name, I call it id to xv. Well, I call it, it's in the hot book, id to xv. I tried to use exactly the same symbols as the hot book. Okay, so my next goal is to define H apply and to define id to xv. Okay, so H apply. Well, I've already said what I should do. I should reduce my problem to the case where this proof of equality is actually the reflexivity. So I need to find a proof that F is homotopic to S. But this is easy. There is the proof that F is homotopic to F is maps X to ref X, because, sorry, it's not ref X, it's ref Fx. Yes, because we need to prove Fx. Yes, this is a typo here. Okay, so nothing complicated here. For the E to XV map that goes from A equals UB to A equivalence, the type of equivalences between A and B is a bit more tricky, because I need to produce all the ingredients of B-inv, okay? So remember that in B-inv, so I should, maybe I should go back to B-inv. Yes, here. B-inv is a set of 1, 2, 3, 4 components. And you have a fifth component, which is the F. Okay, so we need to produce all these material. Okay, so we need to, starting from a proof P, that A is equal to B. Yes, here. We need to produce a 1, 2, 3, 4, 5 ingredients, which is the function F, the function G, the function H, the homotopy eta, and the homotopy epsilon. Okay, so these are not difficult. First of all, we need to produce a function from A to B. Okay, but we consider the type family, which is the identity on the universe. Okay, so it takes a type and returns the same type. So if we transport, so maybe I should write it here. You have your P, you have your universe U here, you have your B, and you have your P here. And we look for a function from A to B, okay? But what is above A is the type A. What is the type family associates with A? It's the identity, so it's A. We have A here, and the type sitting above B is B, because it's the identity. So transport. Remember that transport goes from the fiber here to the fiber here. So it's really a function from A to B. So this is my candidate. The function from A to B is going to be defined by transporting along the identity family, relative to the identity family along P. And this defines the function from A to B. And now to define the function from B to A, of course, I take the inverse of P, which provides me with the function of the right type. And then what I need to find is to make sure, okay, so then I will repeat this function twice, because actually what I'm going to prove is that Q inv holds, okay? But if Q inv holds, I also by inv holds, so I will repeat this twice, here and here. So I need now finally to find the two homotopies. So I need to find a homotopy that goes from the transport here, composed with transport here. Now we know by definition that this is equivalent, this is homotopic. Well, we have seen that it is homotopic to transport along P concatenated with P minus 1. Okay, but P concatenated with P minus 1 is equal to ref. And there is a lemma here, which I will not detail, but here, okay, I have detailed it on the slides. There is also a lemma that says that if I know to prove that two paths are equal, then I have a proof that transporting along P is homotopic to transporting along Q. So if you believe this lemma, then it is safe to do this step. Okay, so this step is first to transport along P concatenated with P minus 1, but P concatenated with P minus 1 being equal to ref, this is homotopic to transporting along ref, which by definition of transport is the identity function. And same game for the other homotopy. So this is a careful definition of a function that goes from this type to this type whose inhabitants are quintuples. Okay, so now I should give you names. Did I give the names? Didn't write the names. So the inverse, the quasi-inverse, which is assumed here, is called UA. Okay, so this function here that goes from here to here, it will be called UA, which means univalence axiom. And I don't remember if there is a name here. There should be a name, but I don't remember what is the name used. Okay, so how much time do I have? Yeah, I have quarter of an hour. Okay, so what can I do now? Okay, I can start a first nice theorem that uses univalence. So I will not have the time to prove it, but I will have the time to state it. Okay, so this theorem is very much related to a very big name in mathematics, which is Alexander Grothendieck. So he's probably the most famous mathematician of the previous century. So it's related to something called the Grothendieck construction. And fortunately, in type theoretical terms, this construction is extremely simple. So it can be explained easily. Okay, so what is this about? So I don't know in which sense I can start. Yeah, I'll probably start with here. Start here. Consider a type family, namely a function from Y to U. Naturally associated with this type family, I can build something that is called in topology the total space. So I can collect all the Py's when Y varies over capital Y. I can collect them together in a sigma type. So I can form sigma Y Py. Okay. And this is a new type. And there is an obvious map from this type to Y, namely the first projections. First projection, because the elements here are a pair of an element of Y and an element of Py, but if I just take the first projection, I get an element of capital Y. So you see that starting from a type family, I get a map from some type here to Y. Now, conversely, suppose that I have a map to Y from some X. Then I can build a type family from Y to U. So you see that I go really the inverse way. Okay. So how do I do this? By taking fibers. So what is a fiber? Well, in the naive theoretical sense, the fiber of function f at some element of y is, in the naive set theoretic term, it's the inverse image of y in X. So it's a set of all elements of X that are mapped by f onto y. Now, type theoretically, it's a bit more involved because we are not doing set theory. It is a sigma type formed by taking a pair of an element of X and a proof that f of X is equal to y. And here you see the difference. So it's called actually a homotopy fiber, because it doesn't mean that f of X coincides with y. So it's not a definitional equality, it's a propositional equality. Okay. So it's called a homotopy fiber. So, okay. So now the theorem that we want to show where is my theorem? Yes, here's my theorem. These two transformations that map a function into y to a type family indexed by y, and conversely that take a type family indexed to y and turns it into a function into y, are organized in a way that yields an equivalence. Okay, so here's the theorem. The type of all functions from y to u, so the type of type families indexed by y, is equivalent to this type here, which is the type of a pair of a type x and a function from x to y. Okay, so this is often called, in the symbol comes from category theory. Okay, and for those of you who know about this, this is the slice category. So in the slice category, you fix a codomain and you let the domain vary. So the claimed inverses for this construction are the ones I just mentioned. So to map, to go from here to here, we take an inhabitant of this type. So it's a pair x and f, a pair of a type x and a function from x to y. And we map it to the family fib f. Remember that fib f here was defined for each y. So it's a type family. Conversely, given a type family, we build the total space and take the projections, and this is a pair which belongs to this type. Okay, so now obviously, I do not have time to give you the proof of this theorem. So I will start tomorrow with the proof of this theorem, and I will use the 6 minutes to do something else. Because I don't think I have real time to. No, I don't want. This is too technical after almost 3 hours. So I will not start to prove this theorem. The only thing that I want to make you aware of and to excite you about is that the proof of this theorem involves univalence. Okay, so this is an incentive to follow this proof because it's a good illustration of this axiom. Okay, so since I'm not doing that, and since I have 5 minutes, I'll start to do what will occupy us most of the time tomorrow, which is to understand the structure, how rich types can be. Do they look like simple propositions that are either true or false? Do they look like sets that may have many inhabitants, but no structure other than the inhabitants? Or do they look like groups, or more precisely groupoids? That means that they have elements, but they also have paths between these elements. Or do they look like two groupoids, etc.? So this is what I'm going to do in the last 4 minutes to give you some definitions. So I will say that a type is, I don't know what happens here. I don't know my, yes, okay, sorry. So I will say that a type is a proposition, and sometimes, sometimes one insists in saying that it is a mere proposition, mere in the sense that it's not more than a proposition, but well, if I just say proposition, it should be enough. So I say that a type is a proposition if the following type is inhabited. I don't know what happens with my pointer here. Okay, so anyway, it's not so important. So yeah, if this type is inhabited. So what this type says is that all elements of the type are equal. So if you think naively, it means that if all the elements of a type are equal, it means that this type has at most one element. Either it has 0 element or has 1 element, but it cannot have 2 because they have to be all equal. But there could be no element. And this looks like a proposition, okay? Because a proposition might have a proof, in which case it has an inhabitant, or it might be false, and then it doesn't have an inhabitant. So and that's all what matters about a proposition. You are not, if you are doing ordinary logic, you are not thinking that there are notions of paths, okay? Sorry, yes, that you're not thinking, yeah, you're not thinking that you are happy with the fact that your proposition is true or false. Okay, if it's true, it's inhabited. If it's false, it's not inhabited. And if it's inhabited, that's all you want to know about it. You don't want to study the structure of proofs of this proposition. So this is the idea of a proposition. Now, there is another notion which is even stricter in some sense, which is to be contractible. So a type is contractible if you can find an element and a proof that all other elements are equal to this element. So it's very similar to being a proposition, because you know that all elements are equal. So we will show tomorrow that any contractible type is a proposition. But here I have an additional information that it is inhabited. So contractible, from the naive theoretical and set theoretical point of view, says that you have exactly one point somehow. But this is not the interesting fact. The interesting fact is that it really says contractible in the sense of topology. So let me finish with this, okay, in just 1 minute. This expresses the notion of contractibility in the following sense. So you have your type A here. You have a point in A. Let me call it A. This is a guy here. This is a guy here. I don't know what. Sorry, but why does it? Yes. Okay. Here you have your guy A here, and then you know that for all elements. So here for all y, so this is my y. You have a path from A to y. No. Sorry. No, D2. Okay, D2. Yes, you have a path from y to A. Sorry, it's difficult to finish in 1 minute when something goes wrong for some reason. Okay, you have a path from y to A. And then you think that you can do this for every element. So what does it mean? It means that the whole of the type A can be contracted to this single point, because I take every point, and remember this idea of deforming the path to go to A. So all the type can be sent to just one single element. And this is what contractible means in topology. A space is contractible if it can be contracted to one point in this sense. And here is the end of the course for today. So bye-bye, see you.